Assalamualaikum and very good morning. My name is Muhammad Saifuddin Khan bin Nazaruddin. I'm from Group 1. My group members are Aina Alia binti Abdullah, Ahmad Diauddin Arif bin Shihabuddin Arif, Darshana anak perempuan Hari Krishnan, Divya Lashmi anak perempuan Puendra. So we are going to present about experiment 6, which is torsion of bars. Moving to the abstract, the experiment was being carried out in order to study the relationship between torque, angle of twist of a circular cross, and the property of material bending moment when subject to different load. The equipment was being used as a base frame and a short shaft. A base frame has a clamp at one end and a ball bearing in a housing plumber block at other end, while a short shaft in the bearing has a 3-jaws jug facing the clamp and the torsion head at the outward side. A hanger cord was wound around the torsion head with an effective diameter of 75 mm. Specimens in the form of length of the rods were gripped by the fixed clamp and the rotating chuck 450 mm away. An arc-shaped scale of degree was mounted on a base that can be moved along the length of a specimen. A pointer on a spring steers registered the rotation of the specimen when a load was applied to the hanger cord. The data was collected and the graph of the angle of twist versus torque was being plotted. The modulus of rigidity was calculated and compared with the theory. The conclusion was derived based on the calculated data and graph. However, our result may differ from the theory due to some errors during the experiment was conducted. Next, for objective is to investigate the relationship between torque T and the angle of twist of a circular cross-section specimen and to determine the modulus of rigidity G of materials. I'll pass to my next teammate.
Hello, I'm Dilakshmi Goyal and will now be explaining the theory and related application of this experiment 6. Shearing strain is measured by the change in the angle formed by the sides of that element. It follows that the length of the shaft is multiplied with the shearing strain will be equals to the angle of the twist times by the P, where the P is the length of the center at any point of the circle of the shaft. Therefore, the shearing strain can be equated with P, where the length from the center or at any point in the circle of the shaft, multiplied with the angle of the twist over the length of the shaft. It also follows that the shearing strain is maximum on the surface of the shaft where the P is equals to C. Therefore, the maximum shearing strain is equals to the C, where the C is the radius of the shaft, multiplied by the theta, where the theta is the angle of the twist, over L, where the L is the length. Consider the case of the shaft of the length L and uniform cross-section of the radius C subjected to a torque T at its free end. The angle of the twist and the maximum shearing strain are related as maximum shearing strain will be equals to the radius of the shaft multiplied with the angle of the twist over the length of the shaft. In the elastic range, the yield stress is not exceeded and where in the shaft. The Hooke's law applies and the maximum shearing strain will be equals to the maximum torque over G. So, the angle of the twist can be equated with torque exerted on the shaft multiplied with the length of the shaft over J, where the J is the polar moment of the inertia multiplied with the G. G is the modulus of rigidity. That's all from me. Now I'll pass to the next presenter. Thank you.
Hi, Assalamualaikum and good day everyone. My name is Aina Alia binti Abdullah and I will proceed with the methodology of this experiment. First step, the aluminium alloy rod is clamped in position and the load hanger on the cord is placed. Next, the rotation scale and pointer set at 400 mm from the fixed clamp and the pointer is set to 0. And then a load of 40 Newton is added by 5 Newton increments and the twist of the specimen for each increment is recorded in table 1. Then the lot then removed and the rotation scale and pointer is set at 200 mm from the fixed clamp. Then the first and second steps are repeated. After that, the specimen changed to the steel rod and the procedure repeated for the 400 mm length only. The readings recorded in table 2. And then finally, the nylon rod clamped in position and the twist for 400 mm and 200 mm is measured when the load up to 40 Newton by increments of 5 Newton is applied to the torsion head. The reading is recorded in table 3, the load removed, and then the observation if the full elastic recovery is occurred or not was made. Next, the diameter of the rod in the table according to the type of materials was measured and recorded. Thank you.
Hi, my name is Darshna Krishnan from Group 1 and today I will be talking about the results and discussion for Experiment 6 Torsion of bar. So first we have here are the results for aluminium alloy rod. The table below is table 1 data for aluminium alloy rod. We have their hanger load in Newton, the torque over 400 mm, the torque over 200 mm, and the twist of rod over 400 mm and over 200 mm. So 400 mm and 200 mm are the lengths of the rods used. To get the torque over the respective lengths of rod, we just have to multiply the torsion head effective diameter, which is 75 mm, divided by 2 to the hanger load force, and that is how we get the torque. Next, we plot the graph, which is angle of twist versus torque. I think we can note here that the equation for the 400 mm rod is y equals to 0.0098x minus 1.4286, while the equation for the 200 mm rod is y equals to 0.0049x minus 0.7143. Next, based on our discussion, we were asked to calculate the modulus of rigidity of each rod. So the modulus of rigidity for aluminium alloy rod is as follows. From the graph, the slope gradient equals to angle of twist over torque. Like I said earlier, from the equations of each graph, the gradient for the 400 mm rod is 0.0098 and the gradient for the 200 mm rod is 0.0049. The modulus of rigidity of materials, G, equals to length of rod over gradient of graph times J. J is second polar moment of area of cross-section, or it is simply known as second moment of inertia. To calculate J, it is just, for a solid rod, it is just pi over 2 times the radius of rod to the power of 4. So that is how we calculate for our aluminium alloy rod. J equals to pi times the diameter provided, which was 6.31 mm, over 2 to the power of 4, and the entire thing over 2 again. And we get 155.687 mm to the power of 4. So over here we calculate the G for torque over 400 mm and torque over 200 mm, and the G we managed to get was 15,021 Newton over mm square for torque over 400 mm and 15,021.185 Newton over mm square for torque over 200 mm. The G average is still the same. Next, we have the results for steel rod. Table 2 shows the data for steel rod. The torsion head effective diameter is 75 mm, while the diameter of steel rod is 4.99 mm. The data provided is hanger load N twist over 400 mm, while we had to calculate the torque. The torque calculation is, as mentioned earlier, it is just the torsion head effective diameter divided by 2 times the force. Next, we plot the graph, and we can note here that the equation for this graph is y equals to 0.0106x minus 3.2321. The modulus of rigidity of steel rod is as follows. From the graph, the gradient we got is 0.0106. So the modulus of rigidity of G, the modulus of rigidity of materials G equals to length of rod over gradient times the second moment of inertia. First, we calculate the second moment of inertia, which is pi times 4.99 mm, which is the diameter of the steel rod, divided by 2 to the power of 4, and the entire thing divided by 2 again, and we get 60.87 mm to the power of 4. So the torque over 400 mm and the G we managed to calculate is 35,520.06 Newton per mm square. Finally is the result for nylon rod. So table 3 shows the data for nylon rod. We have the hanger load and the torque over 400 mm and the torque over 200 mm. The twist of rod respectively over 400 mm and over 200 mm. The diameter of the nylon rod is 6.525 millimeters, while the torsion head effective diameter is 75 mm. The torque is calculated using the formula mentioned earlier. This is the graphs we managed to plot for both 400 mm and 200 mm nylon rod. So the equation for the 400 mm nylon rod is y equals to 0.0069x plus 7.72, while the equation for the 200 mm nylon rod is y equals to 0.0051x plus 3.35. The modulus of rigidity of nylon rod is as follows. From the graphs we plotted, the gradients we got were m equals to 0.0069 for the 400 mm nylon rod and m equals to 0.0051 for the 200 mm nylon rod. As follows, we just calculate the moment of inertia using the diameter of the nylon rod. So diameter of nylon rod divided by 2, 6.525 divided by 2 to the power of 4 times pi, and the entire thing divided by 2, and then we get 177.960 millimeter to the power of 4. So again, we calculate the torque over 400 mm. We calculate the G for torque over 400 mm, and the G we get is 18,664.272 newtons per millimeter square, and the G for torque over 200 mm is G equals to 12,625.833 newton per millimeter second per millimeter square. Now to the discussion part. The question asked is, to what extent does the experiment verify the torque over twist formula based on the graphs plotted? So based on the graphs plotted, it can be noted that the angle of twist is directly proportional to the torque. As the angle of twist increases, the torque produced increases as well. It can be observed from the graph that the longer rod lengths produce a steeper slope, where m is bigger. This indicates that the torsional angle is directly proportional to rod length, i.e. doubling the rod length doubles the torsional angle. Finally, from our calculations of G, it can be said that a smaller angle of twist produces a bigger modulus of rigidity. So to simplify everything, the angle of twist is directly proportional to T, torsion. The angle of twist is directly proportional to L, which is the length of rod, and the angle of twist is indirectly proportional to the modulus of rigidity. Hence, the formula angle of twist equals to TL over JG is valid.
Okay. Assalamualaikum. My name is Ahmad Arif, and I'll continue the conclusion. In conclusion, angle of twist of a circular cross-section specimen is directly proportional to torque. The modulus of rigidity of aluminum alloy rod, steel rod, and nylon rod is 155.687 millimeter power of 4, 60.870 millimeter power of 4, and 177.960 millimeter power of 4 respectively. Hence, with these findings, the objective of the experiment is met. Thank you.